Hi everyone. So in this video, we're going to go ahead and discuss HR diagrams, which are a tool that is commonly used when comparing different types of stars. So HR diagrams actually stands for Hertzsprung-Russell diagrams, which are two different scientists who worked on creating these graphs. And they are actually a scatter plot showing the relationship between a star's temperature and its brightness, which we also know as its luminosity. So when we compare those things, we start to see there's patterns on where stars appear. So let's go ahead and talk through what these diagrams show us. Okay, so along the y-axis, which remember is the vertical axis of our graph, we are describing the luminosity of the star in comparison to our sun. So a luminosity of 1 indicates the star is as bright as our sun. So if I kind of draw that imaginary line in going across from left to right at a luminosity of 1, all of those stars would have about the same brightness as our sun. Now, anything that is above that green line is going to be brighter than our sun, and anything that is below that green line is going to be dimmer than our sun. So if I have a luminosity of 10, this means the star would be 10 times brighter than our sun. Now, this particular graph actually has 10 squared, so 10 times 10, which is 100. So anything along this line would be 100 times brighter than our sun. Similarly, a luminosity of 0.1, remember anything less than 1, means that the star is not as bright as our sun, and it's going to be dimmer. So the sun is brighter than the other stars. So if I go along this line, which is 10 to the negative 2, or 0.0111 of a brightness when compared to our sun. Along the x-axis, so that horizontal axis, we are describing the surface temperature of the star in Kelvin. And Kelvin is just a temperature scale like Fahrenheit or Celsius, but it's actually the official one of the International System for Science. Now, one unique thing about HR diagrams is the temperature actually decreases as you go from left to right. So usually as we go from left to right, things increase, but in this case, it's backwards. So the temperature decreases as you go from left to right. Okay, so when we plot stars according to their brightness and comparison of their temperature, we start to see some patterns emerge. So along the middle of this graph, kind of going from the top left corner to the bottom right, we have this band, which includes the main sequence stars, the stars that are taking hydrogen and forming helium. So we can see it here in that gray band going across that picture. So one thing to note here is that large, higher mass stars are brighter than smaller, lower mass stars. So those that are in the top left corner are going to be hot and bright because they're large, and those that are in the bottom right are going to be smaller and dimmer. And also, as mass increases, so does the star's temperature and its brightness. And then finally, larger stars are going to die more quickly. They're going to get into the final stages of their star life because they burn fuel faster. So they're going to go ahead, use up that hydrogen, get to the helium, and then they're going to run out of fuel much faster than the smaller ones. So we notice above the gray band, so above that main sequence of stars, we have the supergiants and the giant stars. So supergiants have the highest luminosity, meaning they're going to be high up on the top of the graph because they're burning up their fuel very, very quickly. Now, supergiants and giant stars overall are less dense than the main sequence stars. This is because as we get those giant and supergiant stars, we have the outer shells which are expanding, so they become less dense. Because they are less dense, these types of stars also tend to be cooler. Okay, so supergiant and giant stars tend to be onto the middle or the right-hand side of our graph. Because remember, we go from high temperature on the left to low temperature on the right. And then finally, dwarf stars, which are the remains of those small main sequence stars, those tend to be found below the main sequence band. This is because they're much dimmer. They're not having that energy they're giving off to give them the brightness. Okay, so let's go ahead and work through some potential example problems you could see with an HR diagram. Okay, Rigel B is what type of star? So the first thing we want to do is actually locate Rigel B on our HR diagram. So it is right there in that green circle. So if you look, it's kind of along that middle band there. So that means it's going to be a main sequence star. So the middle band of the HR diagram. Okay, so the next one, which star is brighter, Betelgeuse or Rigel B? So again, we want to start by identifying the stars. So here we have the two of them. And then brightness. So remember, that's along the y-axis. So as we go higher up, the stars get brighter. So this means that Betelgeuse will be brighter than Rigel B. Okay, which type of star is Sirius B? So then we're going to go ahead and locate the star on our HR diagram. We see it's in the bottom left-hand corner, so it's going to be below that main sequence diagram. So it has a low luminosity, less than 1, meaning it's not as bright as our sun. So this means it's going to be some type of a dwarf star. And then finally, which star is hotter, Betelgeuse or Rigel A? So again, we want to go ahead and identify the two stars. So they have pretty similar luminosities, but we want to think about where they are along the x-axis. So left to right, where are they? So Rigel A is further to the left. So that means that Rigel A is going to be hotter because we go from left to right, temperature decreases. So Rigel A is hotter than Betelgeuse. Okay, so I hope that helps explain HR diagrams. Once you get to know them, they're not as difficult as they seem. If you have any questions, please let me know. Otherwise, thanks for watching, everyone, and have a great day. Bye.